Okay, here in Lesson 4, we're going to talk about the probability of two events, that's called a compound probability, occurring, and we're going to specifically talk about the OR case and its special situation, which is called the disjoint or mutually exclusive events case. To consider that, it's best to look at an example like this. Let's say if we have a jar, and it has 4 red balls, 3 yellow balls, and 1 green ball, and we're going to remove a single ball. We want to know what's the probability that that ball is red or yellow, and we'll look at a lot of probabilities leading up to that. Okay, so there's really two different ways we could list the possible outcomes in the sample space for this experiment. One would be to list each individual ball as an outcome. So if that were true, then the possible sample space would be we could get the first red ball, the second red ball, the third red ball, the fourth red ball, or the first yellow ball, the second yellow ball, the third yellow ball, or the green ball. Those would be the possible outcomes. And since there are 8 balls in there, and they're all equally likely to be drawn, then the probability would be 1/8 of each case. So each probability would be equally likely at 1/8. Okay, so we could find various probabilities of different events. We could find the event probability, the probability that we have a red ball. So if I did that, we're going to use the equally likely cases scenario because these are all equally likely at 1/8. Probability of the number of outcomes in the event divided by the number of outcomes in the sample space. So if I were to look at the probability of a red ball being drawn, the event sample space has 4 red balls out of the total of 8, and that would be 4 out of 8. So the probability of red is 4 out of 8. If I were to find the probability of yellow, then the event sample space has 3 balls in it. There's 3 yellow balls, so 3 out of 8, and the probability would be 3/8. If I wanted to find the probability of red or yellow, then the event sample space would have a total of 7 balls because there are 4 red balls and 3 yellow balls, a total of 7 balls out of the 8 outcomes, so it would be 7 out of 8. Probability would be 7 out of 8, and that is definitely a correct way to compute the probability of red or yellow. Note that the probability of red or yellow is not a compound probability. It's still a simple probability because it's the probability out of the entire sample space. Okay, but there's a whole other way we could choose to list the outcomes. Rather than the individual balls, we could just list the colors, right? I mean, if the balls are all indistinguishable from each other, I could get a red ball or a yellow ball or a green ball. But if I choose to list the sample space this way, red, yellow, green, then the probabilities are no longer equally likely. And that's okay. We could just say the probability of red is 4/8, the probability of yellow is 3/8, and the probability of green is 1/8. That's a valid probability model, 3 outcomes with their probabilities, and they're all adding up to 1. So let's explore using this sample space to answer the question, what's the probability of red or yellow occurring? So we should be able to use these probabilities to compute event probabilities, including the OR case, and I'm going to put the probabilities over here on the side that we found from using the other equally likely listing. We know these probabilities are correct. Okay, so if I wanted to find the probability for red, or if I wanted to find the probability for yellow, then the probability of red would just be the probability of that one outcome, which is 4/8, and the probability of yellow would just be 3/8, and those match exactly what we had when we analyzed this before with the equally likely case. The real question is, how do we figure out the probability of red or yellow, the case red or yellow? So this red or yellow case is called a probability of a compound event, and that's because 2 things have to occur, right? It can be red or yellow. Maybe I should not say 2 things have to occur, but we can call the outcome successful if we have a red or a yellow. So there's multiple ways for it to occur. So that's referred to as a compound event. And it would be nice if we could somehow combine the individual probabilities for red and yellow in some way in order to get that event. Okay, well, because this event is successful if either red or yellow is successful, or is selected, that means that there's now 2 ways for the event to be successful. So that means that it should be more likely that red or yellow occurs than the individual probabilities of red or the probability of yellow, because now there's 2 ways to get that. And it makes sense that we could try adding the probabilities for this OR case. So let's try that. We could say, is it true that the probability of red or yellow is equal to just the probability of red plus the probability of yellow? Well, the probability of red was 4/8, the probability of yellow was 3/8, and if I add those, they have a common denominator that's 7/8. And sure enough, that is exactly what we saw when we found it the other way with equally likely cases listed for each ball. We know the probability should be 7/8, so it does seem to work. It seems that if you have an event or another event which can happen to be considered successful, you can just add the probabilities. But it turns out there's a catch. To see why, let's consider the same sort of a calculation, but for this scenario we're going to do a single roll of a fair six-sided die. So the outcomes are 1, 2, 3, 4, 5, or 6, and they're all equally likely at 1/6. So if I were to restrict myself to finding simple probabilities of single events, like say the probability that the roll is even, that would be, I could come up with an event sample space. Even consists of the outcomes 2, 4, and 6, and so that's 3 out of the 6 cases. So there's a 3 out of 6 chance of getting the probability of getting an even roll. Right? I could do some other single event, like say the probability that the number that I roll is divisible by 3. Well, the outcomes 1, 2, 3, 4, 5, and 6, the only ones which are divisible by 3 are the 3 and the 6. That's 2 items in the event sample space, or event space, compared to 6 in the sample space, so 2 out of 6 chance of getting a roll that's divisible by 3. So if I want to find the probability of a compound event, like the probability, say, that a roll is even or it's divisible by 3, then we should be able to use equally likely cases, or we should be able to add the individual event probabilities. So if I went the equally likely cases approach and found an event space for even or divisible by 3, it means I should go through the list of all the outcomes and include them in this event space if they're even or they're divisible by 3. So let's do that one at a time. 1, well, that's not even, and it's also not divisible by 3, so we can't include that. The 2, that one is even, so we're going to include that in the event space. 3, that's not even, but it is divisible by 3, so we'll include it in the sample space. 4, that number is even, so we'll include it. 5 is not even, and it's not divisible by 3, so we won't include the 5. And 6 is even, so we'll include that as well. So that means the event space has 4, and that means that the probability of even or divisible by 3 is 4/6. And we're pretty confident, because we built that by hand by looking at, scrutinizing every individual outcome, that that's the true probability of even or divisible by 3. It's 4 out of 6. Okay, but if I took the adding probabilities approach, we know that the probability of an even roll is 3/6, and the probability that the number is divisible by 3 is 2/6. And we found with the other case, we think we should just be able to add these probabilities, right? The probability that a roll is even or divisible by 3 should be the probability of even plus the probability that we're divisible by 3. So if I took 3/6 and I added 2/6, I get 5/6. But wait, that's not the same as 4/6. So it doesn't look like adding worked in this case. It turns out there's more to the story. Okay, to see what's going on, it's helpful if we look at the situation with a Venn diagram. So if I look at the 6 possible outcomes, and I have 2 circles here, subsets for the 2 cases, having an even roll and having divisible by 3, right? The even circle here has the events outcomes 2, 4, and 6 in it, and the divisible by 3 number has the 3 and the 6 in it, which means the 6 is really in both events. It's in even and it's in divisible by 3. And the 1 and the 5 are on the outside because they're neither even nor divisible by 3. So we can kind of see the problem, right? The reason why this didn't work to just add it up is the 6 here is in the middle, so it ends up getting counted twice. And that's the reason why the probability from adding ended up being too large compared to the probability for 6, because we ended up double counting that 6. Okay, that wasn't a problem in our example with the colored balls. So here's the Venn diagram for the dice scenario, but here's the Venn diagram for the balls, right? If we have red and yellow as the events we're studying, then the reds are in the red circle and the yellows are in the yellow circle and the greens are outside, but there's no overlap. There's no way that I can draw a ball and have it be red and yellow at the same time. Since there was no overlap there, then it worked to just add the probabilities. We didn't have an overlap, so there was nothing wrong there. The good news is it's easy to fix this problem. If we want to have an OR case compound event formula, we can just add the probabilities. We just have to remember to subtract off anything that's overlapping so that it doesn't get counted twice. Okay, so the overlap right here, this overlap of 6 here, really that's the probability that the dice roll is both even and divisible by 3. So the overlap is the intersection, which is the and situation, right? So another way to write the correct the corrected OR formula would be the probability that something is even or divisible by 3. It would be the probability that something's even plus the probability that's divisible by 3. We would have to subtract off the probability that something's even and divisible by 3. Right? And using our OR and AND symbols, the union symbol is the one for OR and the intersection symbol is the one for AND, you could write it this way. The probability of even or divisible by 3 is the probability of even plus the probability of divisible by 3, but minus the probability of even and divisible by 3. So some people correctly memorize that for probabilities OR equals addition, that we should add probabilities in OR cases. That idea is correct, but for us to have it work in all cases, it really needs to be modified slightly. It should be OR equals addition, but subtract off any overlap. So here is the true OR formula that works in all cases. The probability of an event A or B occurring is the probability of A plus the probability of B minus the probability of A and B occurring. That's the true OR formula. Okay, so that's the one that we're going to use in so many examples. It's one of the major formulas that's used in solving probability problems. Okay, but in some special cases, like in our jar with colored balls, we don't have any overlap to subtract. That's really a special case of the OR situation, so we have a name for that. If two events have no overlap, then they're called mutually exclusive events, or sometimes we call that disjoint events. Right? So if events are disjoint, then the following is true. The probability of A and B is 0. And that means that the OR formula simplifies, because if I go back to the OR formula, if this probability out here is 0, it means we have a simpler version of the OR formula that just adds the two probabilities and doesn't have to subtract anything. So in the event that events are disjoint, the probability of A and B is 0, and that means we have a simpler version of the OR formula. Okay, to help us visualize this, here are some generic Venn diagrams for two events. We could either have events that do have overlap or events that don't have overlap. So if events do have overlap, then we refer to them A and B as non-mutually exclusive events, or you could call it not disjoint events, or you could call them joint events. They have what's called a joint probability, a probability in the middle. And that probability of A and B is something other than 0. Right? If we have events that don't have overlap, then that means A and B are called mutually exclusive events, or we could say they are disjoint events. And that means the probability of A and B is 0. And so the two versions of the OR formula, right, we have the probability of A or B in general is A plus B minus the overlap, but in the mutually exclusive case, it simplifies to just A plus B because there's nothing to subtract. Okay, just to summarize it again, right, here's the OR formula. Probability of A or B is probability of A plus probability of B minus probability of A and B. And the special case is called mutually exclusive or disjoint. Picture this, and then that means the formula simplifies by removing the last term. We could also define something maybe called a test for disjoint events. If we want to test to see if two events are disjoint, we can just compute the probability of A and B occurring, and if it's 0, it means there's no overlap. All right, that's everything for compound events or cases. You can look at the examples to see a bunch of examples worked out, or you can move on to the next video, a lesson, which is about the compound event situation where we have AND cases.